In this lecture, we'll explore data analysis with SQL. In today's information management systems, just operational applications are not enough. They need to also support a wide variety of other business requirements that typically involve some level of analytical processing. So these requirements can range from data enrichment and transformation during ETL, which is the extract, transform, and load, creating time-based calculations like moving averages, moving totals for sales reports, performing real-time pattern searches within log files in order to build what-if data models during budgeting and planning exercises, and so on. So developers, business users, and project teams can choose from a wide variety of languages to create these type of solutions to meet the requirements. However, many companies have found that the use of so many different programming languages to drive their data systems creates a number of different problems. For example, it decreases the ability to rapidly innovate, creates data silos, results in application level performance bottlenecks, drives up costs by complications, and increases the level of investment in training. So the dev teams need to quickly deliver new and innovative applications that provide significant competitive advantage and drive additional revenue streams. IT and project managers also need an agile platform to underpin their projects and applications so that the devs can quickly and effectively respond to the different changing business requirements without incurring the issues listed above. And with the advent of big data, we are now seeing terabytes and even petabytes of data that needs to be stored, processed, and quickly analyzed in real time as well as via batch and so on. In order to address these kind of problems, some of the traditional large companies like Oracle and Microsoft have enhanced their existing RDBMS systems with analytical tools. So they either created a separate system for data analysis or they created plugins for their regular RDBMS system for it to handle these extra data analysis type jobs. And also, these are not necessarily totally new. This is also supported in Postgres, which what we'll be using for the rest of this demo and lecture. And also, these are compliant with the standards. The key benefits of doing that is there is enhanced developer productivity. So using the latest inbuilt analytical SQL capabilities, devs can simplify the application code by just replacing the complex code that's written in either SQL or even other languages and keep everything in one specific language. This also provides better manageability. So when computations are centralized and they're close to the data, then there is less inconsistency and the ability to access a consolidated view of all the data is simplified. It provides a minimized learning effort. So the amount of effort required to understand analytical SQL is minimized through the use of careful syntax design. Most of these enhancements that are used in these analysis services type products are ANSI SQL standard extensions. So this ensures that there is broad support for these features and there's rapid adoption of newly introduced functionality across applications and tools. Then finally, there is improved performance. So using these data analysis type tools is a lot better and a lot more efficient than using workarounds and using tools that are already built into the traditional SQL. So there are 4 elements in SQL processing. So these are existing SQL features which are used to provide developers and business users with a framework that's both flexible and powerful in terms of the ability to support sophisticated calculations. So there is processing order, the result set partitions, calculation windows, and current row. This is a 4-step process. So the processing order is where the query processing uses analytical SQL, and that takes place in 3 stages where you have all the joins, where, group by, and having clauses are performed. Then the result set is made available to the analytic function and all the calculations are applied. And then if the query has an order by clause, then this is processed to allow for precise control of the final output. The second part is the partitions. SQL allows users to divide query result sets into ordered groups called partitions. So any aggregated result, such as sum, average, and so on, are available to these analytical functions. Partitions can be based upon any column or expression. A query set may have just one partition holding all the rows, a few large partitions, or many small partitions with each holding just a few rows. Then you have calculation windows. Within each partition, there's a sliding window of data that can be defined, and the window determines the range of rows used to perform the calculations for the current row. The window sizes can be based on either a physical number of rows or a logical interval, such as time. The window has a starting row and an ending row, and depending on its definition, the window may move at one or both ends. So for example, here we have a rolling 6-month window with the window start and window stop, and this shows the concept of a rolling window for calculating the moving average. So we'll see all this in detail in a bit. So the concept of a window is very powerful and provides a lot of flexibility in terms of being able to interact with the data. A window can be set as large as all the rows in a partition, and at the other extreme, it could just be a single row. Users can specify a window containing a constant number of rows or a window containing all rows where a column value is in a specified numeric range. Windows may also be defined to hold all rows where a date value falls within a certain time period, such as the prior month. And finally, we have the current row. So each calculation performed with an analytic function is based on a current row within a window. The current row serves as the reference point determining the start and end of the window. Hierarchical database model. A hierarchical database model is a data model in which the data is organized into a tree-like structure. The data is stored as records, which are connected to one another through different links. A record is a collection of fields, and each field contains only one value. The type of a record determines which field the record contains. The hierarchical database model requires that each child record has only one parent, and each parent record can have multiple child records. And in order to retrieve data from a hierarchical database model, the whole tree needs to be traversed starting from the root node. A hierarchical query is a type of SQL query that handles this hierarchical model data. Hierarchical queries can be implemented by using the recursive common table expression, or CTE. A common table expression is a temporary named result set. This is derived from a simple query and is defined within the execution scope of a select, insert, update, or delete statement. The CTEs can be thought of as alternatives to the derived tables like subqueries and views. Common table expressions are supported by Microsoft SQL Server, Oracle, Postgres, MariaDB, MySQL, SQLite, HyperSQL, and H2. In Oracle, these are called subquery factoring, so there might be a little difference in the naming convention. The way to implement the CTEs in SQL is by declaring a with. A CTE can contain recursive references to itself, and it can be seen as a temporary table or a view that's private to only the specific query. So the syntax here is with recursive and then with query, and then you specify the query with the column names and then a select statement. So on the example on the right, you can see, for example, if you want to list all numbers from 1 to 100, then you can use the with recursive and then the function name as values 1, and then you union this with a select statement. So in this case, you're bringing in the n from the top and plus 1 from, and then the function where n is less than 100. Finally, you do the select star from that temporary table that you just created, and then you order by n, so you get 1 to 100. So here, on the left, we can see what the formal explanation looks like for this recursion. So IT is the intermediate table, WT is the working table, and RT is the result table. So these are the three separate tables. The first step is to initialize. So you have the intermediate table is initialized as an empty set. You execute the non-recursive query, assign results to both the results table and the working table. Then the second part is to execute the recursive query itself. So you replace the recursive self-reference with the working table, assign results during execution to the intermediate table, append IT to RT, replace the working table with the current intermediate table, and then truncate the intermediate table. So this is the values union select n plus 1 from for width and where n is less than 100. And finally, you check the recursion. So you repeat the second part multiple times, in this case 100 times, until the working table is an empty set, and you finally return the results table. Window functions. A window function performs a calculation across a set of table rows that are somehow related to the current row. The whole idea behind window functions is to allow you to process several values of the result set at a time. So you see through the window some peer rows that are able to compute, and you're able to compute a single output value from them. This is comparable to an aggregate function, but with window functions, you do not cause rows to become grouped into a single output, and instead the rows retain their separate identities. So you can see here in the diagram, you have a row set, and this is the select intermediate result after having the before, after having, and before the order by, which is where you need to put these partitions. So the window function breaks the select result into many parts called partitions. So in the diagram here, so we can see that there is a result set, and then it's being partitioned into 4 partitions here, and then each of those partitions are being ordered. So these partitions may have an inner ordering which is different from the final result ordering. Now behind the scenes, the window function is able to access more than just the current row of the query result. So all aggregate functions you already know can be used against a window frame rather than a grouping clause. So you can already use the sum, min, max, count, average, and any of the other ones that you might use. There is a default window frame, and the database engine is able to iterate through the result rows, and then it retains the separate identities. Now the real magic of what's called the window functions is actually the frame of data that can see when using the over clause, and then its partition by and order by frame clauses. You need to remember that the windowing clauses are always considered last in the query, meaning after the where clause. So determining the partitioning and ordering of a row set before the associated window function is applied. So this determines the partitioning and ordering of a row set before the associated window function is applied. The over clause defines a window or user-specified set of rows within a query result set, and a window function then computes the value for each row in the window. So you can use the over clause with functions to compute aggregated values like moving averages, cumulative aggregates, running totals, or the top n per group results. You can see the basic syntax for the over on the right hand side here. It's over and then partition by clause, the order by clause, and then a row or range clause. Let's look at an example here. So we have a table here with ID, name, salary, and category. So you have different employees here with their salary, and there is a category. And we just want to take note that this table has thousands of employee records. So the task is to display a table with the employee information, the minimum, maximum, and average salary of the employee category, along with every employee row. So the solution for this SQL query is going to be select star minimum salary over report by category, average salary over report by category, max salary over report by category from the employee table, window report by category as partition by category, and then we limit to 5 rows. Now this is what the results looks like. You have the employee, you have the ID, name, salary, category, min, average, and max. You have the ID, which is the employee ID, employee name, the salary, their category, and the minimum, average, and max. So these minimum, average, and max are calculated based on the entire record set, but partitioned by the category. So for each category that an employee belongs to, we first calculated the minimum, average, and max, and then provided that data in addition to the employee records. Now to explain that, there are 3 steps here. So the first part is we created a window called report by category, and then we are specifying that we want to partition by category. So this is all the way below the from. The second part are the aggregates that we are creating. And we are saying that we want the min salary for this specific window, average salary for this specific window, and the max salary for this specific window that we defined. And then finally, we're also saying that we want to see the data per employee. So we don't want just one big aggregate per category or something like that. So we want to see each employee, as well as we want to see the min, average, and max. So we can see that the windowed aggregate function is newly calculated for each row within the partition based on all rows between a starting row and the ending row. Here's another example from a table with books. So we want to select all the books and compare its price against the average price and the total price of all books per language. So here we have a different number of books and they're in different languages, and there's a price per book, and then we want to calculate the average and sum. So using the select statement on the right, we have title, language, price, and then we have 2 aggregates here, average price and sum price. And then we are saying over this specific window, and we define the window as the name my window, and then partition by, and then the language, which is the English or German. So the results here that you're seeing, the average is per the language, so for everything that's in English, and the sum is also for everything that's in English, and then the second part is the average for everything that's in German, and then everything that's sum for everything that's in German. Now there's another class called the rows and ranges that we add to the window function, or the over function rather. So this further limits the rows within the partition by specifying a start and end points within the partition. So this is done by specifying a range of rows with respect to the current row, either by logical association or by physical association. The physical association is achieved by using the rows clause, and the logical association is by the range. So the rows clause limits the rows within a partition by specifying a fixed number of rows preceding or following the current row. And the range clause logically limits the rows within a partition by specifying a range of values with respect to the value in the current row. Preceding and following rows are defined based on the ordering in the order by clause. The window frame range current row includes all rows that have the same value in the order by expression as the current row. So for example, the rows between 2 preceding and current row means that the window of rows that the current function operates on is 3 rows in size, starting with 2 rows preceding until all the including the current row. And these are further divided into range unbounded preceding, range between unbounded preceding, rows unbounded preceding, and between unbounded preceding and current row. So the range unbounded preceding selects all rows from the partition startup through the last pair in the order of its ordered by clause. The range between unbounded preceding and unbounded following is used to select all the rows in the partition. The rows unbounded preceding is specifically to ignore duplicates, and the between unbounded preceding and current row is the same as the first one, which is the unbounded preceding, but in this case we are talking about row. So please pay attention to the row and the range here. Those two are separate. That might sound a little confusing, so let's recap. Logically, a windowed aggregate function is newly calculated for each row within the partition based on all rows between a starting row and an ending row. Starting and ending rows might be fixed or relative to the current row based on these different keywords. If it's unbounded preceding, that means all rows before the current row, and this is fixed. Unbounded following means all the rows after the current row, and this is also fixed. X preceding means the X rows before the current row, so this is relative. And then Y following means that the Y rows after the current row, which is also relative. And we can use these for different types of calculations. For example, when both starting and ending rows are fixed, the window consists of all rows of the partition, which is the group sum or to aggregate plus detail rows. If one end is fixed and the other is relative to the current row, then the number of rows increases or decreases, so that way you can calculate the running total or the remaining sum. And finally, if the starting and ending rows are relative to the current row, the number of rows within a window is fixed. So that's basically the moving average or over n rows. Now let's look at another example here. This is the example that we can use to calculate the average amount in a frame of 3 days. So this is also in Postgres. So here we have this function here. We're using the with data TA as values 1, 1, 2, 5, 3, 3, 4, 5, 5, 4, 6, 11. Select TA average over order by T rows between 1 preceding and 1 following from data ordered by T. So here we're creating a temporary table with these values 1, 1, 2, 5, 3, 3, and so on. And then we are using an order by T rows between 1 preceding and then 1 following. So 1 above and 1 below the current row. Calculate the average amount in a frame of 3 days in this case. So this is what the result looks like. So you have the inputs, the values, the 1, 1, 2, 5, 3, 3, and so on. And then the third column is the average. So here you can see the explanation. The first row is 1 plus 5 divided by 2 because there are only 2 elements here. The second one, we have 1, 5, 3 divided by 3. So in this case, we're looking at the second row. So 1 above and 1 below. Then the third one is 5 plus 3 plus 5 divided by 3. So that one is the 3, 3 row, where we're looking 1 above and 1 below. So it's 5, 3, 5, and then divide by 3. Now let's look at a different example. So the same input, and in this case, we want to look at what the rows between unbounded preceding looks like. So the frame's lower bound is infinite in this case because it's unbounded preceding. So this is what it looks like. You have the sum 1, 6, 9, 14, 18, 29. So if you have guessed, this is basically the running totals that we are calculating. Now so far we looked at rows, but what about range? So range means all the values in the current range and those before or after, including the gaps. So preceding you have, which is the get rows before the current one, following get rows after the current one, and unbounded, when used with the preceding or following, it returns everything that's before or after. So wait, that sounds the same thing, right? That's the same as what we just talked about with rows. So what's the difference? So we saw that the rows option relies on an offset in terms of the number of rows with respect to the current row. So this doesn't address any gaps. So if you want to get the last 3 months of activity for something, that may span for more than 3 months. Or it could be the other way around. The frame itself can include rows that could represent a period of more than 3 months. So using the form rows between 2 preceding and current row, this will give you what you want only if there's an assurance for no gaps between the months of activity. So that's what the range option is there to resolve by defining the offsets from the current row's value as opposed to offset in terms of the number of rows. So the range frame extent supports the unbounded preceding, unbound following, and the current row as delimiters. So as we can see here, this is using range. So here we're doing a select title, language, price, and then average price over order by language, and then the range unbounded preceding from book. So here we can see that if you look at the average, the first one is the same. So for the English, if you just add up those three prices and take the average, you'll get 76.66 recurring. But for the second part, for the German, if you add up those three price numbers and divide by 3, you won't get 74.166. You'll get 71.667 or something like that. So in this case, the actual data is not shown here, but it's taking duplicates into consideration as well. So in this case, you'll get a different result set, and it might be more useful where the rows is going to eliminate all the duplicates and give us a different number. And here's a visual representation to finally understand this. So the superset is the over, then you have partition by, and within the partition by, you have the result set. So in the result set, the yellow highlighted one is the current row. Then above that, you have unbounded preceding, and below that, you have unbounded following. And then you can see the 2 after the current row is the 2 following. And finally, you can see the rows unbounded preceding are the ones that from the current row going all the way up. That's because you're counting from the current row. Now the row number numbers the output of a result set. It returns the sequential number of a row within a partition of a result set, starting at 1 for the first row in each partition. The row number is a temporary value calculated when the query is run, so this doesn't persist. So you can see the example here. We're doing a select row number, and then we're using the over as row, title, language, price, and then we're using the average price over my window and some price over my window as previously done from book, and then the window we're defining as my window, partition by language. So here in the result, we can see that we have a new column at the beginning called the row number, which provides the sequential number. Now there's some things that you need to note. There's no guarantee that the rows returned by a query using the row number will be ordered exactly the same with each execution unless the values of the partition column are unique and the values of the order by columns are unique, and the combination of values of the partition column and the order by columns are unique. So the row number is non-deterministic. Now there is a brother to this row number, and that's the rank function. This returns the rank of each row within the partition of the result set. The rank of a row is 1 plus the number of ranks that come before the row in question. So the row number and rank are similar, but the row number returns all rows sequentially, for example 1, 2, 3, 4, 5, 6, 7, and then the rank provides the same numeric value for ties. Rank is also a temporary value that's calculated when the query is run, and it doesn't persist. If 2 or more rows tie for a rank, then each tied row receives the same rank. Now the rank is 111 and 444 here is because we are partitioning by the language, English and German. So in terms of the rank, it's just looking at this as just 2 big segments, and it's ranking the entire partition here. So it's the first one is the first rank, and then the German is rank 4. So what are some of the practical reasons for what we just learned? So first one is enhanced reporting. So you can use windowing, lag lead, and the reporting aggregate functions to compute moving and cumulative versions of sum, average, count, max, min, and many other functions. They provide access to more than one row of a table and remove the need to use multiple self-joins. The functions can be used only in the select and order by clause of the query, and the windowing aggregate functions include the first value, which returns the first value in the window, and the term last value, which returns the last value in the window. The lag and lead functions can be used to compare values within a dataset when the relative positions of row can be determined in advance. Pivoting operations. Pivoting is a key technique in many data warehouse related applications. BI queries typically transform multiple input rows into result sets that contain fewer and generally wider rows. The data returned by business intelligence queries is often most usable if presented in a cross-tabular format, and the pivot clause of the select statement lets application developers write cross-tabular queries that rotate rows into columns, aggregating data as part of the rotation process. Prior to this feature, BI tools and report developers were forced to use self-joins as a workaround. Data declassification for reporting and time series calculation. So data is normally stored in sparse form, that is, no value exists for a given combination of dimension values and no row exists in the fact table. So in some cases, it may be necessary to view the data in a dense form with rows for all combinations of dimension values displayed even when no data exists for specific data points. So the data dedensification is a process of converting the sparse data into dense form, and you can use the partition by clause to logically partition the rows in the query based on the expression. The result is a much richer data set that's easier to use in terms of applying analytical functions such as moving averages and moving totals. Data sampling. Some business intelligence reports and advanced analytical processing often need to limit the number of rows returned by the query, either by asking for a specific number of rows or a percentage of rows. So this type of query is often called a top-N query, and it offers a straightforward way of creating reports that show who are the 10 most profitable customers. It's also useful for user interfaces that provide the first few rows of a dataset for browsing. Advanced SQL aggregations. You can use rollup, which calculates the multiple levels of subtotals across a specified group of dimensions. Cube calculates subtotals for all possible combinations of a group of dimensions and calculates a grand total. Grouping, which helps identify which rows in a result set have been generated by a rollup or cube operation. And grouping sets, which is a set of user-defined groupings that are generated as part of the result set. Statistical analysis. Many data warehouse and operational projects start with an evaluation of the available data to determine if the business requirements or hypotheses are even feasible, and which data points are likely to provide the most value. This is also data exploration, and this requires the use of mathematical features like the percentile distribution, standard deviation, linear regression, and many other statistical tests. So a lot of these tools like linear algebra, linear regression, and the statistical aggregates for hypothesis tests are libraries that are provided by these tools. And you can make use of these libraries directly through SQL statements. Pattern matching. There is now inter-row pattern match capabilities which provide extra search capabilities for pattern matching, specifically the match recognize clause, which builds on the syntax used by other SQL functions and features, reusing many of the basic concepts such as partition by and order by. The match recognize clause uses these concepts to logically partition and order the data stream ready for analysis. There are 4 basic steps for building a match recognize clause. You can define the partitions and ordering needed to identify the pattern encapsulated within the stream of events, and define the pattern of events and pattern variables identifying the individual events within the overall pattern. Define and measure outputs, which are the source data points, pattern data points, calculations, and aggregates related to a pattern. And finally, determine how the output will be generated. So this is almost like a data pipeline. So we are analyzing a data pipeline with streaming data here. Spreadsheet-like data modeling and what-if analysis. So there is a model clause which allows businesses and business analysts to create a sophisticated multidimensional array from query results and then apply business calculations, which are rules, to this array in order to derive new calculated values. These values and rules can range from simple arithmetic operations to complex and sophisticated requirements like recursive simultaneous equations. It's able to create this multidimensional array by mapping the columns of a query into 3 groups: partitions, dimensions, and measure columns. These elements can perform a number of different tasks. The partitions define logical blocks within the result set in a way similar to the partitions of the analytical functions. The dimensions identify each measure cell within a partition, which identify the characteristics including the data points such as date, region, and product name. And then measures are equivalent to the measures of a fact table in a star schema. So they typically contain numeric values like sales units or cost. So there's 3 stages here. So the stage 1 is to map the columns to model entities. So this divides the source table into 3 components: partition, dimension, and measure columns. Stage 2 is to define the required business rules that define the new data points. And finally, stage 3, which merges the data with calculated rows. So here, this creates a unified output by applying the rules to the source table to create a unified data set containing the original data and the hypothetical data derived from the business rules. All of these features, and especially the model clause, are all query optimized in order to take advantage of parallel query processing that powers most of these specific engines that are built for data analysis for big data type applications.